So the reason you colonize is either because you just want to have a second base, or because you're mining in space, or because of tourism, or it's because of the science interest of space, or some such reason as that. And I can't see in the near future that people are going to be going into space just because they're looking for somewhere to live, though we will see that a little bit further into the future then that might actually happen. And it's going to be quite a challenge living in these habitats, wherever they are, where you have colonization. So this is the diagram, and this shows, in a rough schematic way, it shows the ISS and the systems that are used for life support in the ISS. And you can see all these different, huge number of machines and different things going on, so CO2 removal, temperature and humidity control, and control of the various gases in the atmosphere. And there are many gases that build up in the atmosphere, a lot more than you would think of. And there's a huge, long list of the various gases, by no means all of them in that diagram, that can build up in a human habitat, and then they all have to be dealt with. So you have, I think, hydrogen cyanide, acetone, methane. This goes on and on and on. And you have to have machinery to deal with all these things and make sure that none of them build up to be in any way dangerous to the human beings. And then you have the human waste. Oh, sorry, I didn't mean to go back. So then you have the human waste, and in case of urine, then this can be recovered to water. So it's not such a big deal. But in the case of excrement, then the ISS, this is simply put, all the excrement is simply put into the supply vessel. And also the same, they are unable to wash their clothes in the ISS. So if you need clean clothes, then you just put your old clothes into the supply vessel, and it goes back and it burns up in the atmosphere, and new clothes will get supplied to you. And then the same thing, you have that there's lots of things get vented overboard. So you've got hydrogen, and you've got carbon dioxide, and various things get vented overboard or are returned in the supply missions. So the ISS is absolutely nowhere near being a self-contained system, and you also have all the problems in the ISS that there have been many teething problems. It seems to be more or less stabilized now, but it wasn't so many years ago where they had some quite major problems with maintaining the oxygen, and they actually had to have oxygen sent up to the ISS from the Earth to keep going, even though they had redundant systems there. So that's the ISS, and this of course is what you probably think of when you think in terms of a space habitat, and you think of not having any machinery at all, and you just have these plants, and these manage to keep everything in order, and you have a closed ecosystem. And this is it's not just a greenhouse, this is the interior of Biosphere 2. So this was actually an attempt to set up a closed ecosystem, a very large one, such you might have in a huge space habitat, and to have a few human beings living inside this and try to get it to work. And sadly it didn't work. But they learnt a lot from it, but they weren't able to keep it completely closed, even with all the research they put into it, and all the effort to try and make it work, and all the plants they got from different parts of the world and so on. However, this is probably just a case of advancing knowledge, and eventually these very complicated things here may eventually get replaced by something much more like that. And then, if we look rather further ahead, then you may get something like this in space, as you get to the larger habitats in space. Now this was a proposal, and it was a serious proposal in the 1970s, and this is called the Stanford torus, and it was worked out in all engineering detail and everything. And they worked out that it would be possible if the United States, just the States, not needing to be collaboration between different countries, if they made a really mega project of it, much as they did with the landing on the moon, then they would be able to build this sort of habitat in space. And to give an idea of scale, this is a river there, and you would have you'd have buildings and so on, tiny, a little bit hard to see in this picture, but you would have buildings and things in there as well, and people would be living across on the floor of this, and the actual floor area would be measured in square kilometers. And then you have multi-story houses on top of that. And they figured out that they reckoned that this habitat, it would eventually pay for itself. And the way that they made it pay for itself was by exporting solar energy, building satellites that in space to generate solar energy, which would then be beamed back to Earth. And very clean energy, which would be available already all over the Earth, and especially it would bring energy to the poor people on the Earth, because they would have this abundant energy from space, and they reckon this would impact the poor people most of all, and help them with energy supply issues. So this was the idea of these somewhat idealists, the Stanford torus engineers, and so this had this idea, and this would work economically. So they would be building these satellites, selling them in order to get, and they would break even, but it was rather a long time scale. I think it was something about 50 years before they began to start breaking even, and then they'd be paying back the costs of the whole thing as well. However, that's talking about using 1970s technology. And obviously our technology has advanced considerably since then, so it would be much more feasible now, surely. And from time to time, people come up with this idea of these space habitats, and they redesign them in different ways. This original one, this habitat, it was designed with, they had the idea. Now the thing that requires the most bulk for your space habitat is the cosmic radiation shielding. And this has to be quite deep in meters, and there's a lot of weight to it. And in the case of the Stanford torus, the way they worked this out is that they decided that it was just too much of an engineering challenge to try and make the whole thing rotate. You would have needed to have had lots and lots of stays, like a suspension bridge, basically, cutting right across the centre of the habitat to try and keep all that weight. And they decided it made much more sense to keep the cosmic radiation stationary and have the interior habitat sort of go through it and spin around through it, very much like a rather fast kind of maglev train or something like that, in the vacuum of space. And it would be travelling at about 200 miles per hour inside this larger cosmic radiation shielding. So that river and that entire habitat would be zooming through the shielding at this great speed. And they reckoned, they didn't go into too much detail about how that would work, but they reckoned that it was a thing that could be sorted out. It was just an engineering challenge that could be solved. Now perhaps we are a bit more safety conscious now than then, and the modern ideas for these habitats, they tend to have the cosmic radiation shielding rotating with the habitat. And to do that, then you have lots of stays going through the habitat in order to help with that. And now I said I'd signpost when it's my own ideas. So this is an idea that I had about these habitats, a way of making it much, much easier to build them. And that is the idea that why do we need to have full gravity? That's what causes all the problems. Because the main things you're going to have in that the habitat, you want it to be self-sustaining and lots of plants in it. So it's mainly a habitat for plants. And it turns out that plants, they manage quite well in 0G. Human beings, then they get very ill in 0G, and you couldn't live in 0G long term. And it's not known what is the lowest G that human beings can tolerate long term. It seems likely that even with low G, at least your muscles would tend to atrophy a bit and be quite hard coming back to Earth. But you might be able to stay healthy, you might not. You have all sorts of problems of circulation and things if you try and stay in 0G, and they have serious problems, for instance,
the things that might impact on the heart because it doesn't have to pump around so much, and you have issues with the eyes. And there was one case of eye deterioration during the ISS which was irreversible. In most cases it clears up, but there are a significant number of people who go to the ISS who they have problems with the eyes at the end of the mission as well. So that's why it's important, as far as we know, it's important to have at least some G, and we don't know how much gravity is needed. So that's why they have these things spinning to have artificial gravity inside. It's for the health of the human beings. But if you think about it, you don't need to spin the entire habitat for that. So why not spin it at a much slower rate? And plants can manage even with 0 G. This was quite a surprise, a study in the ISS, and they had plants growing there, and they found it was thought before the ISS experiments that plants definitely need gravity in order to know which way the roots should go and which way the leaves should grow. But it turns out that when you grow plants in the ISS, then somehow or other, and I think they're still trying to work it out, I'm not sure, they may have sorted it out by now, but somehow or other they managed to figure out how to be able to grow so that their roots go one way and their leaves go the other way, even without any gravity as a guide. So it was certainly possible to have plants growing, and I would suggest you have a low G. Maybe some plants would actually appreciate a little bit of gravity to give them a bit of extra help as to direction, and also to help the gardeners just to have a sense of down, of which way is down, and they don't go floating off so very easily. So I would suggest you maybe have something like 100th G. If you were to do that, then that reduces the weight of the shielding, which it averages 4.45 tons per square meter. This is what they calculated for the Stanford torus was needed, and the figures haven't really changed since then. Basically the physics is still the same as the amount of cosmic radiation shielding that you need. But now if you had it 100th G, then instead of 4.45 tons, you have 44.5 kilograms per square meter. And in that case, well, it seems, why not? You might as well then rotate the cosmic radiation shielding with the entire habitat. And I think that would be a much cheaper way, and also a much safer way of making a Stanford torus. And so then if you do that, and then it's surprising how little material you need to build a Stanford torus. And you can build 3 square kilometers. There's a tiny asteroid. It's a near-Earth object, and it's called Nereus, N-E-R-E-U-S, Nereus. And it is the large, if you're looking at things that are not absolutely tiny, then it's the one that comes closest, it's most accessible to the Earth. It's easier to get to than the surface of the Moon. And it's about 300 meters in its largest diameter. And if you look at the weight of Nereus, the estimated mass of Nereus, there's enough material there to provide cosmic radiation shielding for about 3 square kilometers of habitat in terms of the land area that you can walk on in a Stanford torus. I'm not including the roof there. This is the area you have that's including shielding for the roof, but in terms of the area, I'm counting the area of the floor area. So it is really quite surprising how little material you need in order to build really quite huge habitats in space. And so I wrote this, one of my science20.com articles is called, I can't remember what it's called exactly, but it's saying that there's enough material in the asteroid belt, and including the Ceres, there's enough material to have cosmic radiation shielding for Stanford torus type habitats with a total surface area of 1,000 times that of the surface of the Earth, of the I think it was the land area of the Earth, 1,000 times that. So there's really much more potential for colonization in free space than there is on any of the planetary surfaces in the solar system, unless you want to go troglodyte.
And I'm not talking about living inside the asteroids, I'm talking about simply using the material in order to build these habitats. So that's a definite possibility of colonization, and you don't need to think in terms that you have to colonize Mars. And just to explain a little bit more about this idea, but I don't want to go on too much because I'm getting a bit distracted already, but this is a habitat for plant life, and then when you want to have humans then would come and colonize it, possibly after the plant has been established, and you have a nice circulating atmosphere, and then the human beings then would come and they would build their own habitats. This is my own idea. They have these like observation decks that you get at the top of skyscrapers. It would be like that. You have these rotating habitats, maybe 100, 200 meters across, and you have a little hamlet in it. And you've only got 100 G, so very easy to build these things. And you can easily set it spinning with a nice, quite gentle rate, which is 100 meters across, to get a nice sense of artificial gravity inside your little hamlets. And it really could work quite well. And then you can then set off from, you would even have some kind of acceleration when if you want to set off in your flying car from the outside of your hamlet, or you can go down the pillar. It would be raised above the ground level so you can grow plants underneath it, so it doesn't in any way obstruct the growing conditions. And you have plants inside it, and then you might also have living quarters for the crew. Maybe the whole thing doesn't need to rotate at full G, and maybe it's just where you sleep at night, depending what we discover about human physiology. But anyway, I think that is plenty enough on this idea for now. Unless any of you have questions, then I can talk about it more in some other videos. But now, this sort of thing could also be built around Mars. And this is a picture of, this is a 1980s picture of the idea of using one of the moons of the Mars for resources. So it's either Phoebus or Deimos. I imagine it's probably Deimos. Then there's enough resources in Deimos for cosmic radiation shielding for the entire area of Iceland, twice the area of Switzerland, of once again of these Stanford torus type habitats. So even in orbit around the moon, and then in orbit around Mars, I mean, of course. And there's also the interplanetary superhighway, which is a very easy way by doing gravity assist flybys of planets. You can basically move materials from anywhere in the solar system to anywhere else practically. So certainly from the asteroid belt and from the near-Earth objects, and any of these could be supplying Mars or anywhere in the solar system. And even right out to the Oort cloud eventually. And the Kuiper belt and the Oort cloud. So really you could have colonies in orbit around Mars, and then this doesn't mean that you can't exploit the surface of Mars as well. So I'm taking the long view there. Suppose we decide that we want to keep Mars pristine. Really it's very, very interesting biologically, and we want to keep it pristine for a long time. Then we might start saying, well, we'll just colonize in orbit. And then this is now the whole question though, how are you going to explore the surface if you don't set human boots on the surface of Mars? And this is the solution. And so this is a picture from an artist's impression, and this was done for the 2012 Telerobotics Symposium, which was organized by NASA, and it brought together space scientists together with people from industry who are using telerobotics. Telerobotics, that's when you control something in the distance. So for instance, a rather striking example was when a surgeon in the States, through telepresence, operated on a patient in France. It was a minor operation that he did, but he did do it from that distance. He was in the States and his patient was in France, and a successful operation. And on somewhat shorter distance, after all, keyhole surgery is becoming very common nowadays, and various ways of actually doing surgery, and you don't have to put your hands inside the patient. And so that is also a form of telerobotics, a remote control kind of surgery. And you even thread your surgical implements, down veins or arteries or whatever it is. I'm not a surgeon. There may be something that is completely wrong there, but you surge them. You somewhere or another you thread these even into the heart. And so amazing things they can do nowadays. Well, that's basically the same idea as telerobotics. It's also used for exploring the seabed, of course. So you have these submersibles and they explore the seabed. And it's also used for deep sea drilling and so on. So these experts came together, and also academics at universities who study all this sort of thing academically, and people who are building these various robots and things, and they all came together in this conference. And they strongly advise that if we send an orbital mission to Mars, then we should have telepresence operated robots on the surface. Telepresence is when you're close enough to the surface to be able to operate them in real time, almost as if you were there. And this is actually also quite an old plan to not colonize Mars, but to explore Mars in this way. And it's the HERO is one of the, it keeps being brought up. The Russians brought it up, Lockheed Martin brought it up. It's one of these ideas that is continually repeated, but perhaps its time has now come. So an earlier version of it was the HERO mission, which HERRO, the HERO plan to explore Mars from orbit. And so they had the idea of exploring just like this, and they had you have these people in the spaceship, and they're controlling these robots on the surface, and they have a very clever orbit that they set up to work in this way. And this orbit, it's the Molniya orbit, and on the Earth, again, it's the Russians who use this for their satellites. But in the case of, and it's because of where they launch from and things like that, and also the areas on the surface of Earth they're interested in. But in the case of Mars, it's a very useful orbit. The way it works is that it's not a geocentric, but instead the way it works is that twice a day it goes over the surface of the Earth. In this case, it would go over the surface of the Mars, and it goes quite close. And I think the Russians were most interested when it was furthest away, because it's a very stable position. But here they're most interested when it's close to Mars. And you would arrange it so that every day, twice a day, so the orbit is orientated towards the Sun, and it is called a slowly sun-precessing, almost sun-synchronous orbit. That means almost synchronized with the Sun. You can't do it perfectly because of the irregular shape of the ellipse of the Mars orbit, but you have this slowly precessing orbit, and it's a very long elliptical orbit. It comes close to Mars, and it comes close to Mars at the middle of the day for wherever the place that it's going to be above. And then 12 hours later, again it'll come close to Mars on the sunny side. And then it'll be the opposite side of Mars, of course, because Mars by then has turned around, because it's half a Martian day later. We're talking, it will be every 12 hours and 20 minutes, half the Martian day. And so this is a rather brilliant idea of a way of exploring Mars by telepresence. And the great thing about this, in some ways it's a much better orbit to do for that than one that is close to Mars, given that you're not going to be full-time all the time doing telepresence operations. And then the great thing about it is that it is almost identical to a Mars capture orbit. So if you want to get from the Earth to the Mars, then there are different orbits that you might aim for on Mars. So the low ones that are used for the mapping of Mars, for the photographing of Mars, they're a little bit harder to get into. But if you're just aiming to be captured by Mars, then the delta V that's needed for the Mars capture orbit, which is a very elongated orbit, then the
delta V you need for that is less than the delta V that is needed to get to the surface of the moon. So this means that it's going to be really quite a cheap comparatively, especially compared with the landing on the surface of Mars, then going to one of these almost close to Mars capture orbit. So you've got a very low cost orbit, very low cost mission, and then in terms of science value, you can control all these rovers on the surface. And nowadays you would think of these rovers as being semi-autonomous as well, so they're doing things when you're not controlling them. It's a little bit like the game of Civilization, if you've ever played that or watched someone else playing it. And you can see that they're controlling these people, and they tell these people to, for instance, start chopping down trees, and then they go to another group of people and you say start building houses, and just leave them doing whatever it is they want to do, you want them to do. So it'd be very similar here, that you maybe set one to do some digging, and one of them you set it to start analysing something in some experiment and so on. And so you'd be controlling a number of different rovers. Even each crew member could control a number of different rovers if we can get them to the surface of Mars. And it really makes sense for future rovers to Mars, if they're likely to be there for any length of time. I would say even for ExoMars, it would really make a lot of sense to make sure that it can be operated by telepresence in this way, because there might well be human operations, human missions to be able to do this sort of thing over the time period of these missions. And certainly later missions as time goes on, and depending how optimistic we are and whether we really go for this is the way to go. And so even in the HERO analysis, they worked out that just one mission, a much cheaper mission to this Mars capture orbit, close to Mars capture orbit, it could do as much science value on the surface as 3 missions to the surface. And that's because you don't have to get into your spacesuits. That's a big saving every day. And also you're controlling all these different, you're in office kind of environment, and you're controlling all these different things on the surface. And it's also, by the way, much safer, because if you have an accident with one of your rovers on the surface, well, it's an accident to a rover, it's not an accident to a human being. And it could even potentially be repaired by using pieces of other rovers, which you couldn't very well do with a human being, not on the surface of Mars anyway. And so there you have the human beings up here, and they would have artificial gravity, just the simplest way is a tether system, and they can be protected from cosmic radiation, and you can deal with that using water is quite good, at least especially for a reasonably short-term mission. You mightn't have to worry about these many tons that we were talking about before, and just having having water, the water that they have anyway for drinking water, and they have the fuel for the return journey. And certainly they can be adequately protected from cosmic radiation. The studies were made for these, for HERO and so on, that they could be adequately protected, and from solar flares as well. And actually the way that I would do it, if you asked me to organise this mission, I would send 3 of these spaceships up there for the very first one, as long as you've got humans on board, because then 2 of those will be lifeboats, and you can make sure once you made one, it really hardly costs very much more to make 3 of them, because most of the cost is in the design. And that means that you've got spare parts there, and if necessary, if one of them gets is not non-functioning, you can go back in the other one. And then if all goes well, then you've got masses and masses of living space there. And then you've got all the fuel, and you can send extra food and things in your other spacecraft out there. And so anyway, that's just a suggestion. But so where are we? We've got these, they're controlling the rovers on the surface. Now, one of the advantages of controlling the rovers on the surface like this is that you get the possibility of superhuman powers as well. So, for instance, it's very difficult for a human being to fly on the surface of Mars. But something like this, if we go to the next one, then if this is the, I think it's called the ornithopter, something like that. So in the thin Mars atmosphere, it is quite difficult for a human being, quite difficult for an aeroplane to fly. But the way that the bumblebee flies, apparently that can be scaled up. And on the Earth, a bumblebee flight only works if you've got very small wings, because the atmosphere is so thick. But if you are on Mars, then you can have the same very stubby looking wings, just rather like a bumblebee wings. It really doesn't look very much like a flying machine, but on Mars, if you have this and quite a large unit like that, flapping its wings at great speed like a bumblebee, and use this kind of vortex effect thing, that whatever it is, the way the bumblebee flight works. And so this is something you'd be able to do with your telerobotics. So you'd be able to fly about on the surface with these things. I am wondering whether to make an end of this. Do you mind? I'm just going to look and see what the time is. Oh, goodness me, 49 minutes. I didn't mean to talk so long on this. So I think I will stop now. This is very long for a YouTube video. And then I will continue in the last one with a few kind of wrapping up things and looking a bit ahead. So and I have some nice new, some wild ideas of other ways that you could be able to explore the Mars surface apart from these bumblebees. And then I also want to talk a little bit about the possibility of early life on Mars. But I think I'd better make that a separate video. It's now 50 minutes.